Alright, hello, and welcome to Chapter 4, Section 3. We are going to talk about a few different things here that might be useful in terms of what you're going to see on the Chapter 4 test and essentially a completion of basic probability rules and problems. So, if you've got the notes, and if you need them, they will be attached to the Canvas discussions post where this video is linked. And make sure you get those notes open. The notes start with 3 problems. It says problems to try on your own. What do you know? Numbers 2 and 3 are pretty difficult. I wouldn't necessarily expect you to be able to get those without having talked about them first. But number 1, which is this one here, if you flip a coin 4 times, how many possible results are there in terms of heads or tails? And what I mean by that is getting a head and then 3 tails is different than getting like 3 tails and then a head. So even though those are both 1 head and 3 tails, the order matters. So with that in mind, what I'd like you to do is pause the video for a couple minutes, see if you can come up with the answer to this question. I'm curious to see if you can come up with it without knowing any formulas or anything like that. So pause the video, figure out the first one there. Alright, I trust that you paused the video. I believe in you. If you didn't, this is your last chance. Alright, so we're going to talk about toward the bottom of the page here, what's called the multiplication rule of counting. And this rule makes questions kind of like this one, and like some of the other ones that we're going to see in a few minutes, where the answer is something, a ginormous number. We're going to have, via the multiplication rule of counting, a very easy way of answering questions like that and finding out how many I don't want to say the word combinations, how many possible outcomes there are given that certain things happen. So, the multiplication rule of counting states that, let's say you have let's say that there is some event that happens, some probabilistic event. We'll call it E1, okay, for event 1. Let's say event E1 has N1 possible outcomes. So event E1 has N1 possible outcomes. I'll let you copy that down on your paper real quick. Okay. Then the total number of outcomes would just be N1. But this gets really interesting when there start being multiple events. So let's say there's an event E2. Just make sure I didn't write on my wall here. I think my whiteboard starts about here. I really need a border for this because one of these times I'm just going to write all over my wall and it's not going to be a good situation. Event E2 has N2 possible outcomes. So you can see the pattern here. Each event has its own number of possible outcomes. These numbers do not need to be the same. Sometimes they can be, but they don't have to be. So the first event could have 4 possible outcomes, the second event could have 10. Doesn't matter, but they could both be 4, let's say. And I'll just put ... here. We could have as many events as we want. So event 3 has N3 possible outcomes, event 4 has N4 possible outcomes, so on and so forth. Okay. Then the total number of possible outcomes for the total number of possible outcomes for the entire series of events, 1, event 2, all the way up to, we'll say the last one is EM. We could have made that really whatever letter we want, except N or E. Okay, so this is an arbitrary number. This could be the 6th event, it could be the 24th event, it could be the 1000th event. Okay, however many it is you're looking at. The total number of possible outcomes for all of those events is... Well, event 1 has N1 possible outcomes, event 2 has N2 possible outcomes. So the total number of possible outcomes is going to have something to do with these N's for all these events. And this is called the multiplication rule of counting. It's a big hint. We're just going to multiply all these N's. So N1 times N2 all the way up to NM. So we're just going to multiply all these together, take the product of all those. That is going to be the total number of outcomes for the entire series of events. Okay. So, if you need to pause the video for a second and digest what the multiplication rule of counting is saying, it's a lot of words, but the concept is very simple. Do that real quick. And now that you understand this a little better, I want to revisit this problem. If you flip a coin 4 times, how many possible results are there? Well, one thing you could do, if you didn't know about the multiplication rule of counting, you could try listing all the possibilities that you could get. And for this particular problem, it's not impossible to do that. You could get 4 heads, 3 heads and then a tail. I'm going to try and be systematic about this as much as possible so I don't miss any. You get the first 2 heads and then tails heads. You get heads, heads, tails, tails. Heads, tails, heads, heads. Heads, tails, heads, tails. Heads, tails, tails, heads. Or heads, tails, tails, tails. I think these are all the different results you can get where heads comes first. Those are all the possible results if heads comes first. So now we need all of the ones where tails comes first. So it will be a repeat of all of these, except the first letter will be T instead of H. So I think that's all of them. I don't think we missed any. Okay? If you tried the problem this way, did you get all 16 of these? Or maybe you left one out, maybe you weren't thinking of it really all that systematically, that's fine. Okay? You could write out all these results this way. And the answer is 16. But how else could we have done it now that we know about this? How many events are there in this problem? Event 1 is you flip the coin the first time. How many outcomes are there when you flip a coin once? Heads or tails, that's 2. So N1 is 2. Second time you flip the coin, it's either heads or tails again. So N2 is also 2. Every time you flip the coin, it's going to have 2 possible outcomes, and we're doing that 4 times. So we're just doing this. 2 to the 4th power, 2, 4, 8, 16. This is much quicker. You're much less likely to make a mistake answering this using the multiplication rule of counting. Okay. So it comes in handy for problems like that. Now, there are also 3 examples at the bottom of the page here. So, again, what I would encourage you to do is to try all these on your own. See what you come up with. Then play the video, see what I come up with, and make sure that we're both right here. I could mess up. It's been known to happen. I don't know how to edit videos, so it would just stay in if I screwed up. Okay? So, pause the video if you haven't. Figure them out. Okay, let's look at example 1 here at the bottom. How many possible outcomes when you roll a die 5 times? Okay, I didn't specify how many sides the die has. We'll assume it's a normal 6-sided die. So, the first time you roll the die, there are 6 possible outcomes. Second time you roll the die, 6 possible outcomes. And we're going to do that 5 times. So that's just going to be 6 times 6 times 6 times 6 times 6. You may even want to write that as 6 to the 5th power. This could have been 2 to the 4th power. Whichever way you want to do it. 6 to the 5th power, I don't know that. I do not know 6 to the 5th power off the top of my head. So I will use my trusty dusty calculator. 7776. $7,776 different outcomes when you roll a die 5 times. Okie dokie. So you can see how even with a relatively small number of events, when you're multiplying all those numbers together, this gets out of hand pretty quickly. This number can get really big. But as long as you know how to apply the multiplication rule of counting, you're just multiplying numbers together. That's it. Example 2. Potbelly Sandwich Shop. My favorite place to get a sandwich in Noblesville. Has 8 different soups on their menu, 21 sandwiches, and 7 desserts. And I've had almost all of them, and they're all delicious. So how many ways could you order one of each? Okay. This is a twist on the traditional standardized test problem of Sally has 3 shirts, 5 pants, and 4 pairs of shoes in her closet. How many different outfits can she wear? It's the same problem. It's the multiplication rule of counting. That's all it is. We're just going to be multiplying the number of soups times the number of sandwiches times the number of desserts. So we've got 8 times 21 times 7. Okay, so this is an example where the number of outcomes for each event is different. N1 is not the same as N2, is not the same as N3, but we can still use that rule. So we multiply this together. 56 times 21. Oh man, 56 times 21. Yeah, I'm not willing to do that and get it wrong. That's what calculators are for. Yeah, I was going to say 1,176. I was just checking. I was just checking. 1176 there. So I would say I've probably got at least 100 of these combinations down in my lifetime, and that's why I've got the belly I do. I'm working my way towards this, though. We're getting there. Give me a few more years. All right, so example 3 there. Last example at the bottom of the page. Oh, my bad. On your notes, it just says examples. These are the 3 examples that go at the bottom of the page there. My bad. I thought I had those on there. I don't. How many possible outcomes when you flip a coin 12 times? Okay, so it's a subtle extension of the problem we started with here. If you flip a coin 4 times, we know that the answer is this. So now we're flipping it 12 times. So if you don't really understand the multiplication rule of counting, you might think, well, it's similar to that problem. Something's changing to 12. Is it 12 to the 4th power? No, think about it. The first time you flip a coin, there are 2 outcomes. The second time you flip a coin, there are 2 outcomes. Third time, 2 outcomes. 4th time, 2. 5th time, 2. 6th time, 2. So you're multiplying 2 by itself by however many times you're flipping the coin. So here it was 2 times 2 times 2 times 2 because you were flipping it 4 times. First, second, third, fourth. If we were to write this out for this one, now that we're doing it 12 times, this would be 2 times itself 12 times. I have limited real estate here, and I don't want to write 12 twos, so I'm just going to put 2 to the 12th power. And we need to know what that is. Luckily, one of the days when I was a freshman in college, I was a loser, so I sat in my dorm one evening. This is before I really met my wife, and I memorized the powers of 2 up to a certain point, but I always have to start at the beginning. So it's 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4092, 4096, 4096. Yeah, because 2048, 48 times 2 is 96. So 4096. Don't ask me to go too much higher than that. Freshman year of college was a long time ago. All right. So the important thing here is that you're able to set this up. Okay, you don't need to know how to calculate that in your head. It's a dumb party trick. I don't think anyone would even clap. So the important thing is I'm really multiplying 2 by itself 12 times, because each of the 12 times you flip the coin, there are 2 possible outcomes, heads or tails. Okay, so if you come across problems that look like any of these, that are just asking how many possible outcomes are there when these events are put together, that's the multiplication rule of counting. Just multiply the number of outcomes of each event. Cool. So there's only one more type of problem that I want to talk about in this video. And for this, I decided to draw a tree, which was kind of stupid because I'm really bad at drawing. So I modeled my really bad drawing after a really bad tree, which is a Charlie Brown Christmas tree. Yeah, that's as close as I got. So let's get past my art skills to this problem. You flip a coin twice. Okay, so we're only flipping the coin twice now. What is the probability of getting 2 tails? You may know the answer to that already. And if you're thinking you know what it is, you're probably right. But I want to introduce how to create a tree diagram. And since we might already know the answer to this question, if we draw the tree diagram and we get that as the answer, we'll know that we created it correctly. And that way we can do more complicated tree diagrams in the next video. So, for a tree diagram, for a problem like this, I would recommend making the diagram. It always starts at a single point. It always starts at a single point. You can even label that point start if you want. Okay? We're going to branch out, which is why it's called a tree diagram. It has branches. We're going to branch out from this based on how many possible outcomes there are for the first event. The first event in this problem is the first time you flip the coin. When you flip a coin, how many outcomes are there? 2, heads or tails. We've already established that. So this is going to have 2 branches. One for heads and one for tails. Okay. Now, before we keep branching off, every time you draw a branch, I want you to write the probability of getting that outcome for that event. So, on this branch, going toward heads, what's the probability of getting heads when you flip a coin? 1/2, or 0.5. You could label it with the fraction, or you could put the decimal. It's up to you. Since 1/2 works really well both ways, I'm okay with you putting the decimal there. If you're dealing with a problem that has fractions like 1/3, I would recommend that you keep the fractions instead of writing the decimals, because once you start rounding things, your answer gets less and less correct. But since 0.5 works really well, I think for this problem, I'm going to use the decimals. But normally, I might keep it in fractions. Okay, same thing here. We want to write the probability of getting tails. I didn't tell you it was a fair coin. It is. Okay, so it's 50-50. These are both 0.5. Okay, so this tree diagram right now represents the first time you flip the coin. Now let's talk about the second time you flip. Okay, let's suppose the first time you flip the coin you got heads. Now you're flipping the coin again. What are the possible outcomes for the second time you flip the coin? Heads or tails, right? It doesn't matter that it was heads the first time. It's still just heads or tails. So we're going to branch out twice from there. One for heads and one for tails. We're going to label the probabilities. They're still 0.5. And then from tails, again, this is assuming the first time we flipped we got tails. We're flipping the coin again. How many outcomes? 2. We could get either heads or tails again, with probabilities 0.5 for both. Okay, so this is about as simple as it gets in terms of a tree diagram. We'll do in the next video a more complicated example where these probabilities change. Okay, but this is just establishing what this diagram looks like. You'll start at a point and you'll branch out based on how many outcomes each event has. So, this diagram now represents all the different things that can happen when you flip a coin twice. You get heads and then heads again, heads then tails then heads, or tails then tails. So, what we want to know is the probability of getting 2 tails. So in order to answer that using this diagram, we're really only interested in, from the start, getting tails and then tails again. So I could put the probability of tails and then tails, probability of TT, equals, this is 0.5, and then from here to here is another 0.5. So to calculate these probabilities, you go from the start to where you want to end up, multiply the probabilities along the way because we need tails and tails, and means multiply. So this is 0.5 times 0.5. Which is 0.25. Okay? And that's probably what you thought it was at the very beginning. Okay? The tree diagram shows everything that can happen, and if you're asked about the probability of something in particular, you just need to go from the start to where you want to end up and calculate the probability of the whole event by multiplying. Okay. So again, this is about as simple as the tree diagram gets. We could calculate the probability of getting heads then heads. That's going to be 0.5 times 0.5 as well. This isn't part of the problem, it's just explaining that you can find all the rest. What would this represent? Getting heads and then tails. Also 0.5 times 0.5. This is tails and then heads. Also 0.5 times 0.5. They're all the same. And that makes sense, right? If everything is equally likely, heads or tails on any flip, all 4 of these outcomes should have the same likelihood of occurring. And they are all 0.25 or 1 in 4. But the question that was asked here was only the probability of getting both tails. So it's only that one. Okay. So that's a nice tree diagram intro. I hope you enjoyed learning about the multiplication rule of counting and tree diagrams. In our next video, we will do another example of a more complicated tree diagram, and we might even get into some permutations. Not sure yet. But for today, that's all we've got. So have a great day, and we'll see y'all next time.